All right, everyone, welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington, and today I'm joined by Dan Fu, a PhD student at Stanford. Before we get into today's conversation, be sure to take a moment to head over to Spotify, Apple Podcasts, or your listening platform of choice. And if you enjoy the show, please leave us a 5-star rating and review. Dan, welcome to the podcast.
Hi, thanks so much for having me. Excited to be on.
I'm excited to have you on and looking forward to digging into our main topic, which is your ICLR spotlight paper, Hungry Hungry Hippos, towards language modeling with state space models. But before we dive into that topic, I'd love to have you share a little bit about your background and how you came to the field of machine learning.
So I'm a PhD student at Stanford. I've been in the PhD program for about 5 years now. I think I really got interested in machine learning during undergrad when some of these kind of machine learning models were just starting to kick on. I remember, the ImageNet challenge, the first time that kind of a deep learning model was doing well, kind of doing image recognition. I was like, oh, that seems really interesting. Then when I got to Stanford, there were just so much exciting things going on, and obviously in the past few years, there's just been an explosion of ideas, of energy, and it's never been a better time to kind of be in this space and be doing machine learning. Um, that's kind of how I got here, and it's been a wild ride, but I've been having fun.
It's definitely been a wild ride, and it's definitely an exciting time to be in the space. So good timing for sure. Tell us a little bit about your research interests.
Yeah. So for the past few years, I've really been interested in seeing how can you increase the context length of these amazing models that we've been seeing. So if you use ChatGPT or GPT-3 or GPT-4, there's kind of they can do amazing things. You can talk to them. Sometimes I have them write my emails, but one of the things that you really wish they could kind of have more context about you, about your life. Like I wish it could read all my emails and then write exactly an email the way I would, with my exclamation points and my commas and all those other things. Um, and right now, there's really kind of some fundamental limitations to the context length. So for the longest time, you could only do 2,000 words, which is a couple pages. But I'm sure this conversation will generate more text than that. And when you read a book, there's a lot more in your mind than just 2 pages. So for the past few years, we've just been looking at how to increase the context length. So that's everything from kind of optimizing attention, which is one of the building blocks to all the models these days. And we've seen our work be picked up by industry. OpenAI has used it to increase the context length of some of their recent models, to some of the newer work, and the work that I think we'll be talking about today, where we're just trying to see, is there another primitive, another building block that we could use to build these language models that where you can still kind of get these magical qualities, but then that doesn't scale quadratically in the sequence length, so that it could actually be computationally feasible to show it all my emails, and it say something meaningful about me.
I was going to ask you to elaborate on the challenge a little bit. And you touched on it just then. There's maybe a kind of naive question. Hey, can't we just throw compute at this thing? It's cheap. Why are we stuck at 4K or whatever the context length is? What are the challenges with increasing that?
Yeah. So really the fundamental challenge is that attention, which is kind of this building block that we've used to build all these large language models, it grows quadratically in the sequence length, and there's really a pretty simple reason for that. So attention, it's kind of like a brute force approach to language. So the way it would work is, you have a sentence, and then in order to figure out what a word means, you compare that word to every other word in the sentence. So in order for a GPT model to process this conversation, for example, you'd have to get every single word that you and I have said and then in order to interpret the next word, go and compare every single word to everything that we've said. And obviously, this is not how humans do conversation. Like, I can barely remember which words we started this podcast with. Maybe Sam, you know better because it sounds like you've given that spiel a bit. But in language, we don't need to remember all these things. So that's kind of what gives us hope that there's something that is subquadratic out there that can do language.
And just building on that, do do you take inspiration from the approach that biologic approaches in trying to come up with alternative methods? Like, just hearing you say that makes me think that maybe there's some meta attention mechanism that's like more abstract than attention, or something like. But are you thinking about it from the perspective of like purely, the optimization of computational architectures and structures, or are you also thinking about it from well, the brain is doing something, what's the brain doing, and how can we do something more like that?
Yeah, that's a really great question. So, as an academic, I like to say we can play both sides. So, about a year ago, we really tried this like computational optimization bit, and you can go pretty far. So, I mentioned at some point that I think that for the longest time the sequence lengths were at 2,000, but now in the biggest models they're at 8,000 or maybe 32,000, and because that's partially because we were able to do kind of some systems optimizations to make it so that you can at least fit that into memory. So for 32,000, for example, if you're willing to pay a very, very large cost, you can kind of make that happen. A couple years ago, it would have just been completely infeasible, but now there's kind of some ways to do it. Um, so that's kind of one approach, kind of the systems approach. But like you say, there's a lot of things to take inspiration from. So in Hungry Hungry Hippos, for example, we took inspiration from a lot of kind of foundational work in signal processing. So folks who have been analyzing time series for decades. So obviously, if you're trying to analyze an earthquake time series, for example, you're not going to something sampled at thousands of samples per second, you're not going to do this quadratic thing. So in Hungry Hungry Hippos, we kind of took some inspiration from those techniques, and a lot of it is kind of built on those fundamentals. I'm no biologist. I won't necessarily say there's direct biological connections, but certainly inspiration from great work that people have been doing in the sciences for years.
Okay. Before we get to Hungry Hungry Hippos, you mentioned that we've been able to kind of brute force it using computational optimization to get to 32. Can you elaborate a little bit on uh, some of what that looks like? What are the things that we've done that will get us there, or that have gotten us there?
So there's one work that we put out almost a year ago now called Flash Attention. It was a great collaboration with some really smart folks at Stanford. And there, what we did, there's a couple pieces, but I think the most important one, if we're going to long context, was we made it possible to, even though the compute is still quadratic, you're still doing all this brute forcing. Previous implementations, the memory requirement was also quadratic. So if you train models and you kind of like run your NVIDIA SMI or whatever, classically you increase the sequence length, then those numbers blow up. You run out of space on GPU, and then yeah.
I was going to ask GPU memory as opposed to CPU memory or storage. Okay.
And with flash attention, we were able to take that memory footprint and turn it linear, kind of using some classical systems ideas that have been around, like in the databases community for years. But we were able to adapt some of those techniques and make the memory footprint linear. So you can fit a sequence like 32K, 32,000 onto your GPU now. You're still going to pay that high compute cost, but at least it's feasible to take some existing model that you did most you were training maybe on 2K, something cheaper, and then fine tune it for a longer sequence. So things become a little bit more feasible, but of course, if you want to go from 32 to 64, you're going to pay a 4 times cost there. So there's you can go. it can certainly moved where the state of the art was, but there's still these fundamental limitations to the quadratic brute force approach.
You mentioned that that was kind of applying classical database optimization types of approaches, things like hashing and binary tree or trees or things like that, or other approaches. What specifically did you do?
So in kind of the machine learning parlance, we call it tiling. It's actually even simpler than hashing. So this is, I think, in a databases course, it's almost I think we found it in lecture one.
Like sharding?
Not even sharding, just so you're computing some like matrix multiplication, and then instead of materializing it, you compute it kind of block by block. And in databases, this is kind of classically you're searching through some set of records, or you're doing a join between two tables, and then the naive way to do it is you write down like all the records that match, but instead you can just do it block by block. So it's a it's a lecture one type idea in databases, not even sharding and hashing and all those things, but hadn't been applied to attention yet.
It's kind of it's inspiring, I guess, that we can take these level 101 lecture one type ideas and apply them and make a lot of progress.
Yeah, yeah, I agree. Yeah.
There's certainly a lot of lecture one ideas out there. Hopefully there are a bunch that are as fruitful.
Yeah, yeah. I think, people say that science happens or progress happens when you kind of take ideas from two fields and put them together. And I think this is a great example of, um, you know, the right person in the database community would have known this, but needed to be in the right place and understand kind of what the machine learning bottleneck is to kind of make it happen.
And so Hungry Hungry Hippos, is it equally as simple an application of basic principles, or is it we getting more sophisticated here?
I think it's slightly more sophisticated to the average computer scientist. And I say computer scientist intentionally because I found out recently that some of the primitives that we're building on are actually in first or second year electrical engineering. So it's actually another setting where the right person in the right place could have figured the ideas out. But so I'll get into a little bit more details. But what we're building on in Hungry Hungry Hippos is a primitive called from signal processing called state space models. So state space models or state space representations, these are classically used to kind of model long time series. Um, and they're the type of thing that if you take a signal processing class, actually are kind of lecture one of a signal processing class, but have not been applied to language as much in the past.
Like Markov chains, that kind of thing?
A little bit. You can think about it kind of like some of those recurrent networks, like Markov chains. They have some properties of things like LSTMs as well, if you're familiar with those. But they have a nice mathematical property from the signal processing folks, where you can also think about it as a convolution. So it's one mathematical primitive that is both kind of recurrent and also a convolution. And that kind of lets us do a lot of nice things. So with LSTMs or recurrent RNNs, classically the problem is that there's like these vanishing gradients. You're kind of powering, like running this thing over and over. It can be hard to optimize, hard to learn. A state space model, you can take a recurrent network and then turn it into a convolution, and then compute it kind of with, in parallel with relatively high hardware utilization, and it actually becomes um, more feasible to use to train a large model.
One more kind of high level, kind of overall problem question: is the bottleneck, the challenge, is it primarily train time? Is it inference time? Is it both? What's been the big limitation?
So for our work, it was actually a quality problem. So um, if you if you take kind of a standard state space model and just stick it into language, it doesn't perform super well. So for our work, it was actually mostly a problem of figuring out how can we adapt this kind of mathematical primitive and make it work for language.
But even before we get to the state space solution that you've done in this paper, the general issue of the the quadratic relationship between the sequence length and compute and memory, does that become a limitation at train time primarily, or inference time, or something else?
Right. Yeah. Great question. So it's actually both. So both train and inference. Um, so if you're training a model that scales quadratically in sequence length, in order to get it to kind of learn the long-term dependencies that you'd want from a long sequence, you have to train it for a very long for with very long sequences, and then that's a quadratic blow up. Um, but it's also a problem during inference time, and what I mean by that is so if you take one of these models that has a longer context length and you feed it a very long document, you can actually watch the model slow down as it's trying to produce new tokens. And that's because for attention, every time you produce a new token, every time you say something new, you have to go back and compare it to everything that you said before, every single word. So the longer your document gets, the kind of the more expensive the inference is. So with these quadratic things, it's actually both. It's both training and inference. It kind of become the bottleneck for these models.
Got it. Got it. So let's dig into the next level of detail on Hungry Hungry Hippos and this state space model. So the inspiration kind of came from this second year double E or signal processing context. So you had this idea, right? What was the first step, and where did you run into challenges?
Right. Yeah. So the first step is really okay. We have this primitive that um, that we think should work. You know, it can model time series well. It can model audio well. And I've had great lab mates who have been kind of looking at state space models for years. Albert Gu, Treedow, who's a co-author of the H3 paper. Like we have people who have been using state space models for deep learning for a few years now and been seeing success. Um, but we always ran into this problem where if you just took a state space model and swapped out attention and transformer, so take your standard transformer, swap out attention for a state space model, we see quality. The quality is kind of not up to snuff, and it can be to give some specifics. We'll see gaps of 5 perplexity points, and for some context, that's the difference between like a 100 million parameter model and a 10 billion parameter model. So it's a big gap in quality, um, and it's you know not something that we'd like to see. So there's um, nice computational properties, but it didn't quite give us the quality and the magic that we want out of these language models.
And so something you said in there, the state space model is not it's not supplementing the existing transformer architecture, but rather you're trying to rip out attention and plug the state space model in its place. And the idea being that you're hoping that the state space model accomplishes the same thing, like capturing these long term relationships between tokens, but more efficiently.
Exactly. Yeah. So we want something that doesn't scale quadratically, and can kind of still do these nice language tasks, still model language well.
Yeah. Yeah. And so, how did you overcome this quality gap that you ran into?
So we what we did is we kind of went back to basics and tried to figure out, what is a simple little toy example that we can play with to kind of understand what's happening here. And what we ended up doing is we kind of started putting together these very simple synthetic languages. So very simple languages, like with maybe 20 words in them, and sentences like A, two, B, three, kind of like there's these letters and these numbers, and you try to each sentence will have some mapping from letters to numbers. We call this particular language associative recall. And then the test was simple. It was just, okay, each sentence has this very simple mapping of letters to numbers. I can write a little piece of Python code to solve it. Can the state space model solve it? And what we found is that transformers could do this fine. They would get to 100% accuracy kind of every single time, and things would work out really well. But when we swapped out the attention for the state space model, we found out that it couldn't solve these synthetic languages, which is kind of surprising because it's not a particularly, it's a very simple language. You would think that this powerful primitive can solve it. What we ended up finding was that there's kind of some fundamental limitations in the exact expression of the state space model, and in order to solve it, what we did was the fix was actually quite simple. We just took two state space models and stacked them together, and then multiplied their outputs together. So it was very very simple, but with kind of taking two of them and stacking them together, we were able to figure out, oh, it can actually start doing this lookup. It can say, at the end, you have this letter A that appears, and you can go back and kind of look up what the right value is. Like if there was an A and a 3 that appeared earlier, and then there's an A at the end, you can go back and do that lookup again. And when we started seeing that O can actually turn on these synthetic languages, we then scaled it back up to kind of real language and find that it started to close the gap.
So, is there a specific intuition for why this stacking works? Like, is it? I guess to me, it maybe starts to seem like some kind of sliding window type of approach where uh, you've got a buffer that you're able to kind of compare tokens.
Yeah, so there's kind of two pieces in there. So the comparing tokens, your intuition is exactly right. That's kind of what those multiplicative elements are doing, and we can actually prove that a standard state space model wouldn't capture some of these multiplicative elements. Um, but there's another thing going on as well, which is with the state space model, we can create kind of a store for kind of global memory for the entire sequence. So the state in a state space model refers to kind of some hidden state that you can store, and with that you can actually start to store some of these kind of key value associations that you see, and then recall them for the entire sequence. So previously a state space model on its own, it can do something simple like I will memorize the token that appeared at position 2, but you can't kind of dynamically tell it where to look, what to look back up. That's where the multiplicative interactions come in. So the multiplications, you can think of them as controlling like some sort of direction, some sort of like operator saying where to look, and then the state-based models, with all this great work, all this great history and signal processing, can actually kind of store a memory for a long sequence.
I don't know if this question makes any sense, but do you need the two state space models, or is there some way to make it like self referential, auto regressive, or something like that with just one?
That's a really great question. It's something that we've looked into a little bit, but we haven't kind of fully explored. I think there's actually, now that you mentioned, in some follow up work, we were able to kind of simplify the architecture a little bit. And if you read the Hungry Hungry Hippos papers, there's a lot of kind of stuff about exactly how we set up each state space model. But in some follow up works, we were able to simplify it. And in one of those follow ups, we actually kind of introduced some idea of a recurrence, where we say, you can say one state space model, and you can just think of it as, okay, now it's going to multiply with the next one, and kind of like that. So there's a little bit of that going on. I'm sure, now that it's out there, I'm sure there's a lot of, very smart people who can take a look and see how they like to simplify it as well.
What's the relationship between the number of states in the state space model and the sequence length? Is that a hyperparameter, or is it one to one, or
We actually haven't seen that you need like a particularly large state for longer sequences. Maybe if we scale to hundreds of thousands or millions, the tune will change. But so far in what we've seen, um, the uh, the kind of the state vector size we use is 64, and that's the one that seems to be working so far.
And so, talk a little bit about results and benchmarking. What context sizes did you look at? What it sounds like you use, was it perplexity that you mentioned as the metric? Talk a little bit about what you saw.
In the H3 paper proper, we kind of looked at language modeling at several different model sizes. So in the original paper, the one that we're talking about, we actually ended up keeping two attention layers in there because we saw some better performance. And kind of in follow ups, we relaxed that, took out the last bits of attention.
And we're talking about the state space attention as opposed to the traditional transformer attention.
Yeah. So in the Hibos paper, we have there will be like 30 layers in a transformer. We uh, rip out all the attention and then replace it with the state with the new H3 layer. And then except for like two attention layers, so one at the beginning and one in the middle, that would kind of keep in, and we saw that there was better performance. There's like maybe a minor difference if you take the attention layers out, but the ones that we kind of evaluated at length were kind of this hybrid architecture.
Okay.
So with this hybrid architecture, we found that we could actually outperform transformers in quality, which was kind of really exciting to us, that we could rip out almost all the attention and get something that actually worked better. So some perplexity results. And for those who are listening, perplexity, you can think of it as kind of the exponent of the loss. So it's kind of a measure of how well does your model learn how to model language. We saw that in terms of perplexity, the H3 hybrid models were outperforming transformers. Um, we saw in some downstream evaluations kind of zero shot performance on kind of NLP benchmarks like Superglue. We were seeing that they were outperforming transformers. Um, and that was really exciting to us. Um, Anecdotally, we've heard people say that the models that we've trained seem to be more coherent a little bit than other models of the same size. So we've scaled up to 3 billion parameters so far, which is small relative to the open AIs of the world, but pretty decent for an academic setting.
And when you say transformers, are you did you create a language model from like a generic transformer architecture, or are we talking about some kind of off the shelf named language model, llama or whatever?
Yeah, so we took kind of a generic architecture and we trained our models from scratch. So it's very similar to let's see, Eleuther has a line of models called Pythia, GPT Neo. It was the same data set as that, so they're kind of very comparable to that line of models.
Presumably, then, there wasn't a big focus on kind of optimization and tricks and things like that. You weren't necessarily going for kind of absolute performance relative to other language models. It was more base transformer, then these various modifications, um, and comparing the performance within that set. Is that right? Or did you also benchmark relative to other language models?
So we actually did benchmark relative to other language models. We compared against the original GPT-2 models, the GPT-Neo models of the same size. When we did the paper, like Pythia, Llama, these other models kind of weren't out yet. But yeah, so we did kind of do a head-to-head comparison against those other models, and we, on average, we seem to be doing better than them.
Okay. And is the areas that you performed better, are there qualifications on that better performance, beyond the kind of the architectural things that we talked about? Are there, um, a certain set of cases where it performs better and cases where it performs worse, or, um, anything like that?
Yeah, that's a really good question. So what we found is that in the kind of cases that we tested, it seemed to work pretty well. Um, uh, Obviously, since then there have been, I think, since when we did this paper and now there's been a lot more kind of know-how about how to train these models in terms of fine tuning them, using instruction tuning and doing things like that. So I think if you compare it to maybe a instruction tuned model of the same size, or one of these models kind of fine tuned for chat, the H3 model won't chat with you kind of as well. You kind of have to fiddle with it, prompt it in the right way. And I think the ways that we know how to train things now have evolved quite a bit. So I'm sure that those things are hopefully also transferable.
Yeah, and that thank you for picking up on that. I was trying to get to like transferability of your results to other types of models, and kind of the general problem domain of large language models and context length. And um, it sounds like you do expect transferability. In talking about the results, you didn't. I don't recall you mentioning specific context lengths. Um, can you elaborate on that? I would expect that would be a big part of what you accomplished is, uh, you know, increasing the maximum context length without uh, unacceptable degradation in performance. Is that right?
Yeah, so we have trained our own models up to length 8K, kind of a full training run. In some kind of smaller synthetic examples, we've gone up to 32K, 128K, and some follow-ups. We're working on trying to scale to take those sort of more synthetic examples, bring it to the full language modeling experience. I think hopefully within the next month or two we'll try to release something that where the sequence length is much longer. But we're actively working on it, and very excited to kind of see what the models can do.
Using the same state space approach, or are there other approaches that you have moved on to?
Yeah, so that's a great question. In the in some follow up, so one follow up that I'll mention briefly is called Hyena.
Just kind of going across the zoo.
Exactly. We're looking for the next animal that starts with an H for the next version. um, but yeah, so with Hyena, we kind of I mentioned, I think briefly, that state space models, you can think about them as maybe a recurrence, maybe a convolution. In Hyena, we said, okay, what if we just go with a convolution view completely? And we saw a little bit, we can eke out a little bit more performance. We don't need those last couple of tension layers in there with Hyena. So it's further improvements. I think with Hyena, we're also trying to see if we can get kind of some of those recurrent properties back in there. So it's all kind of orbiting around the same core ideas, but the flavor of the week, the the differences in architecture, we're still exploring, trying to figure out exactly what exactly works the best.
Okay, I'm trying to ask if an 8K context length relative to a small model is equivalent to a larger context length for a larger model. Like, um, is it, or is, on the other hand, would be like, okay, your technique got you to 8K. If you apply that technique in the context of a much larger model, you're still at 8K. Like, is there a scaling of the context length, or is there scaling of the technique's ability to increase the context length with the complexity of the model?
Yeah, so there's a good question there. I think um, I don't have a ton of experience training the very large models, because academic. Someone If somebody gives me a massive cluster, I'll be happy to. But yeah, I think in theory it should all just work, but until I will say until we I'm an academic, until we've tested it, shown that it can actually work. I won't say 100% guaranteed that it'll scale in the same way.
Right. But you're. I guess what I was kind of curious about is like, okay, you apply this technique on a small, it gets you to 8K. If you're applying it on this massive scale model, does it get you to 64K? That's not a claim that you're making here at all. It's
Oh yeah. So I understand your question. They're kind of orthogonal a little bit. Um, yeah. Mhm.
Yeah. Okay. That's what I was wanted to confirm. Cool. Awesome. Well, super interesting work. And you mentioned some of the next steps. We'll be keeping an eye out for them.
Great. Yeah. Thank you. It's super fun. Like I said, great time to be in machine learning.
For sure. Hey, thanks so much, Dan.
Thank you.